Assalamu alaikum warahmatullah. Today we'll be talking about duality. This is an important concept in optimization, especially in convex optimization. Now, looking at this constraint problem that we have here, we learn how to use the KKT conditions to solve the inequality and generally the constraint optimization problems. Recall that we have this form of the optimization problem as we learned earlier. This is the canonical or standard form of the optimization problem. Uh, this is called a primal. It is called a primal problem. So it's the main problem. So how did we do it? We introduced the Lagrange multipliers, but we skipped a step actually in the derivation here. In order to solve it in a rigorous way, we need to identify this indicator function, which means that if x or the input of this indicator function is less than or equal 0, you'll get 0, right? So you are within the boundaries of the function, the domain of x, the feasible area, the feasible range, let's say, okay? If not, you'll get minus infinity. This means that the function will go to minus infinity, which leads to having the minimum value being minus infinity, right? Okay, so this is how the inequality constraint function is formulated into an unconstrained optimization problem. Okay, but the main problem in this indicator function that it is not differentiable, right? You cannot differentiate this function because it is discontinuous. So this is a discontinuous function, hence we cannot differentiate it. So we need to approximate this indicator function. We approximate it by a linear function. Okay, so we multiply the inequality constraint by lambda. Lambda is unknown, so we are introducing an unknown variable in addition to the unknown x that we need to optimize. So which value of lambda we need to find? Logically, we need to find the best value. So in this case, we have a new problem, Lagrange, or which is the Lagrangian. We need to maximize, we need to find the best lambda that maximizes this Lagrangian function in order to approximate the indicator function. Okay, so this is the new function that is used in place of g of x, which is the maximum of the Lagrangian with respect to the lambdas, the Lagrangian variables or multipliers. Okay, so we can find a minimum bound for this function using the minimax inequality. So the minimum of the best Lagrangian is greater than or equal the maximum of the minimum of the Lagrangian. This is called the minimax inequality. Okay, and it is used to find the dual problem. Okay, so the dual problem here is we find, so it is this function, right? So we find in this case the minimum with respect to x of the Lagrangian. So we get this dual problem, and then we maximize the dual problem. So we have two problems now, the primal problem, which is the original problem, and the dual problem. So what's so interesting about the dual problem? The dual problem is the lower bound of the primal problem. So if the prime problem is very complicated, okay, you cannot solve it easily. You can find a lower bound for this problem, okay. And the good news is that the dual problem is concave, so you can always solve it, right? So you can always solve the dual problem and find this lower bound for the primal problem. This is called weak duality. Weak duality. As an exercise, let's take the primal optimization problem. We need to minimize the norm of x such that ax of Ax equals b. So this is an equality constrained optimization problem, right? We want to find the dual problem. We want to find the dual problem of this primary problem. So we apply, the first step is to find the Lagrangian, right? So we will multiply the constraint with the Lagrange multiplier. Then we find the dual problem. We need to minimize the Lagrangian with respect to x. Okay. In order to do that, we differentiate with respect to x, and we set to 0 and find the value of x. Then we substitute back into the Lagrangian to get finally this form here, right? So this is the this is the dual problem. We need to find what? We need to find the maximum of this dual problem, which constitute the lower bound of the primary problem.